Hello, everyone. It's time for our final inner chapter. So today we're going to be finishing up our conversation on naming functional groups by specifically looking at functional groups that contain carbonyls and a nitrile just for fun. So we're going to extend the rules we covered last time to carbonyl containing functional groups. So two of our most common carbonyls that we're going to often see are going to be involved in ketones and aldehyde. So again, ketone is in the middle of a carbon chain, and an aldehyde is going to be at that terminal position with an H also coordinated to the carbon. So each of these show different functionalities and thus have a little different names. So ketones, again, always are going to occur in the middle of a ring or in the middle of a carbon chain. And they tend to have a suffix of -one and a prefix of oxo. Now, aldehydes, they're always going to be that terminal group. So whenever you see them, they're always going to be located at the end of a chain, and you're never going to see them in a ring, but you can also often see them adjacent to a carbon ring. And this will change a bit of how we name them. So they have a suffix of al as in aldehyde, as opposed to ketone, which is -one as in ketone. Now, the fun thing with these guys is they both have the same prefix of oxo. This is one of the reasons why is if you're drawing them, oxo pretty much means throw a carbonyl on it. So you're going to have to figure out whether it's an aldehyde or a ketone based on prefix, simply based upon location. All right, so we can use our same set of rules that we've used for alcohols and aldehydes, but to ketones. And we're going to go ahead and go through increasingly complicated versions. So in our first case, we have an alcohol and a ketone. So the ketone gets our priority. So it's our priority functional group. And so we're going to use that -one ending. And again, we have a 5-carbon chain. So this is a pentane, meaning I have a pentanone. Yay! Now, in terms of numbering, we're going to try and minimize the numbering of that ketone, which means we're going to go ahead and start on the right and work our way left. So that gives that alcohol the 4 position. So this means we have a pentane 2-one. Now we have to go ahead and deal with that that hydroxy functional group, which now becomes a hydroxy group. So this is going to be on the 4 position. So it's 4-hydroxy. Being that that's our only side group, we can put this all together to get a 4-hydroxy pentane 2-one. Now let's go ahead and take a look at our our second species. So in this one, our highest priority functional group is indeed a ketone. And our longest chain that involves both carbons is still that same 5-carbon chain. Because again, we don't care about this nice little 3-carbon branch, which would give us the longest chain of a hexane, because it doesn't include that ketone. So this means that we have a pentane. So big trick here, though, is we have 2 of these ketones, which means that I won't use a classic -one suffix, but instead of a dione, which means I keep that E. So I have a pentane dione. Then we have to go ahead and do our numbering. In this case, if I work right to left or left to right, it won't change. So by arbitrary construct, we're going to move right to left. This means that my side group is at the 3 position, and it is a nice propyl group. Oh yeah, so my ketones are at the 2,4 position. So I have a pentane 2,4 dione, and I have a propyl group located at the 3 position. So this means it's 3-propyl pentane 2,4 dione. All right, now our last one's kind of a fun one because we have a cyclic molecule again this time, but this time we have 3 ketones. So we're still going to have that -one, but it's based on a cyclohexane. The fun bit is that this guy isn't just a ketone or even a dione, it is a trione. Now, one of the key things to watch out for this is when we do the numbering for a cyclic system, we're going to try and minimize the numbers. So you can go ahead and experiment, but the way to minimize all of these ketones is if I put this guy at the 1 position, this guy at the 2, meaning that this guy's at the 4. Alternative versions would be something like 1, 4, 5, 6, which is bad, or 1, 2, 5. So again, it can take a little practice to go ahead and find the way to minimize all of the numbers, but in this case, it's going to be a nice cyclohexane 1,2,4 trione. And again, with no side groups, that would give me the whole molecule. Now, one of the tricks is when we're extending this name nomenclature to aldehydes, one big important thing that comes in is that priority is going to go to the aldehyde, but aldehydes don't need locator numbers because they're always going to be at the one position. Because in each case, they're a terminal group. So they're going to, by default, get that one. So in this first case, again, priority functional group is that aldehyde. So I've got the al suffix and 4 carbons. So it's a butane, meaning I get a butanal. And again, no side groups going through the number. So again, that aldehyde's at the 1 position, but it's always going to be at a 1 position. So name simply is butanal. Then we can go ahead and extend this. So in this case, I have a ketone and an aldehyde. Aldehydes are higher priority than ketones. So again, this is going to still get that al suffix. I have 5 carbons, so it's going to be a pentane, so pentanal. Now, numbering the system, don't need to include the 1 on the al because, again, no, it's already at the 1 position. However, I do have a ketone at the 3 position. Now, this becomes a 3-oxo. And again, oxo could apply to ketones or aldehydes, but that 3 position is internal, meaning that it is a ketone. Putting this all together, I get a 3-oxo pentanal. Now, let's have some fun with a system that contains more than 1 aldehyde. So in this case, priority goes to the aldehyde. So we have an al. We're going to, our longest chain that includes both of these aldehydes is going to be a 4-carbon chain, even though I could make it longer. So this means I have a butane. Now, this becomes a butane dial. Again, keep that E, add in the di. Now, when I go ahead and number this, again, 1, 2, 3, 4, but there's no place for the aldehyde to go but the primary position and the final position. So again, don't need to actually include the numbering into the main name. However, I do have a nice ethyl group at the 2 position, so this becomes added as a substituent, and the numbering is going to be used to minimize that alkyl number. So this becomes a 2-ethyl butan dial. All right, now, one of the big tricks working with these aldehydes is aldehydes can't exist as part of a carbon ring, but they can exist adjacent to a carbon ring. So again, there's only 1 carbon on the side chain, so I'm not going to go ahead and just have a principal carbon chain of 1. So instead, we call this a cyclic aldehyde. Now, these have slightly different namings. So our cyclic aldehydes are going to be named according to a mix of 2 things. We're going to name that aldehyde as a carbaldehyde on the suffix, and the main portion of the name is going to be a cycloalkane or alkene, essentially denoting what ring that aldehyde is attached to. Now, when we're numbering that ring, we're not going to include this the carbon of the aldehyde. Instead, we're going to give our number 1 to the carbon that's attached to the aldehyde. And then we're going to try and minimize the next substituent. So let's go ahead and walk through this name. So I have a cyclic aldehyde, meaning the name is the suffix is really going to be a carbaldehyde. And then my main ring in this case is a cyclopentane. So I can bring this together to have a cyclopentane carbaldehyde. So it's a little bit of a long name, but again, immediately tells me what I'm dealing with. Now, when numbering this, again, that 1 position is going to go to the aldehyde, and then I need to minimize the position of my amino group, so at that 3 position. And because, again, I have an amine as the non-priority functional group, this means it gets used as a prefix, and again, is amino instead of amine. So this would be a 3-amino cyclopentane carbaldehyde. All right. So our next major class of functional groups are called the carboxylic acid derivatives. Now, this includes a wide range of species, and most namely carboxylic acids, acid chlorides, amides, and nitriles. So you might say, what do these guys share in common, especially because three of them are carbonyls and one of them isn't? Well, it actually stems from a topic we'll hit next semester, but it's the fact that all three of these groups, if you treat them in the right conditions in water, you can turn into carboxylic acids. So you can convert an acid chloride into a carboxylic acid, an amide into a carboxylic acid, or a nitrile into a carboxylic acid in water. So then going through how we name them. So starting with the carboxylic acids, which is our highest priority functional group. This has a suffix of oic acid. So anytime you see that oic acid, you immediately know you're dealing with a carboxylic acid. Occasionally, if I need to use it as a prefix, it becomes a carboxy. And then our acid chloride has a suffix of oil acids. So really we're changing that oic acid into an oil chloride. And its prefix is kind of a fun one. It's chlorocarbonyl. Always enjoy that one. Our amides have a suffix of amide. Love it when it's easy. And a prefix of carbomoyl. So again, kind of a fun one. And then our nitrile groups have a suffix of nitrile. Again, love an easy one. And the prefix of cyano. So again, for this one, think cyanide. All right, let's go ahead and try and apply these to different molecules using all of the previous naming rules we've seen. So again, starting with the molecule on the left, our highest priority functional group is going to be that carboxylic acid. So that means that my suffix will be that oic acid. Now, then I need to count my main chain. So 1, 2, 3, 4, 5, 6. So I have a hexane. But wait, there's an alkene in here. So I really have an hexene. So bringing these together, I drop that E and I get a hexanoic acid. Again, big difference in between hexenoic and hexanoic. So pay attention to that. It's an easy one to get caught on. Now, when numbering, the numbering system's gonna put a 1 at that carboxylic acid, meaning I don't need to number it in the name of the molecule, but it will drive the numbering of everything else. Namely, that alkene gets put at the 2 position. So I have a hex 2-enoic acid. Now I still have one more functional group, that ketone at the 5 position, which gets named as an oxo. So it's a 5-oxo hex 2-enoic acid. Now looking at the molecule, now one of the things I have to watch out for is now that I have this alkene in here, I have to evaluate stereochemistry. So in this case, I have an E5-oxo-hex-2-enoic acid. So again, note the fact that the principal substituents on these guys is opposite, leading to that E denotation. So our next one, this one gets a little bit fun because we have 2 carboxylic acids. So that oic acid still gets the denomination. The chain that includes both of these carboxylic acids gets essentially that is a 4-carbon chain. So we have a butane, which becomes a butane dioic acid. So again, we keep that E when I put in that di or tri prefix. Then again, numbering, we're not going to include numbering on the dioic acid because by definition, just like the aldehydes, carboxylic acids are terminal groups. So in other words, so the numbering is mostly going to be about minimizing the numbering of that alkyl group, which again is going to be a pentyl group located at the 2 position. So I have a 2-pentyl butane dioic acid. Now, in this case, I now have to denote whether this guy is R or S. So, because again, I have a denoted stereocenter here. So my priority is going to go to here, then to the acid, then to the other carboxylic acid, then to the long alkyl chain. So this gives me R stereochemistry. So it's an R 2-pentyl butadioic acid. So again, this ending name, these ending names may seem a little bit complex, but when you break them into parts, they really help inform what you have. Now, one of the things that is worth noting is that when I'm dealing with a nitrile, this is kind of an exception because every other functional group, we always drop that E when we're working with the names. Now, because that nitrile starts with an N, this would give us some really weird names. So instead, when I go ahead and add a nitrile suffix, I always am going to keep that ane, ene, ine. All right, so noting that, our first group includes a nitrile. And again, as the only functional group, this means that I'm going to use a nitrile suffix. Then again, my main chain is going to be 1, 2, 3, 4, 5, 6. So I have a 6-member chain, so it's a hexane. So I have a hexane nitrile. Now, again, I have a substituent, so let's go ahead and do the numbering. So again, that nitrile gets the 1 position, but since it's a terminal group, I don't need to include that 1 in the numbering. However, I do need to name my cyclopentyl group at the 4 position. So this is 4-cyclopentyl hexane nitrile. And again, almost all of these carboxylic acid derivatives, they're all terminal, so we're going to be dropping that numbering scheme quite frequently. Now, one of the things to watch out for is when you're dealing with carboxylic, whenever you're dealing with any of these carboxylic acid derivatives, that carbon atom is not going to be included in the numbering when it's a substituent. So we can see this with this nitrile group when I have a mixed acid chloride and nitrile species, because acid chlorides are going to be a higher priority than our amines or our nitriles. So I'm going to have an owyl chloride suffix. And again, because that numbering isn't going to include that carbon, it means I only have a 3-carbon chain. So this means I have a propanol chloride. Now from here, I'm going to go ahead and add that I have a nitrile, which again, as a prefix, becomes a cyano group. And that cyano group is located at the 3 position. This carbon of the cyano is bound to the 3 carbon. So this is a 3-cyano propanol chloride. Now, one of the other things to watch out for is when I'm dealing with amides. Now, one of the reasons why amides are important is because they also, like an amine, can have alkyl substituents. So when we're naming them, we're going to name them much in the same fashion as a secondary or tertiary amine. We're going to name that primary group. Major difference is the primary chain will always be the one containing the carbonyl group. And then the other 2 substituents will be named as alkyl substituents with that N prefix. So for a molecule on our left, this means my primary functional group is an amide. It is bound to a 1, 2, 3, 4, 5, 6, 7 carbon chain system, but it has an alkyne, so this means I have a heptyne. Drop the E and I have a heptynamide. Now I have to go ahead and number the system. Focus is putting that 1 on that carbonyl location, so I don't have to put a 1 before that amide. And then that puts a 3 on the alkyne, so I have a hept 3-ine amide. Then I have to go ahead and name my substituents. Only substituents in this case is going to be an N-methyl group and an N-ethyl group. So again, putting them alphabetically, this becomes N-ethyl, N-methyl. So I have an N-ethyl, N-methyl, hept 3-ine amide. Now, one of the things to watch out for is, again, in each of these cases, we're often going to find branched carboxylic acid derivatives. So in this case, my priority goes to these carboxylic acids. So how do I name this amide? So in this case, we're going to treat that entire amide as a group, meaning it gets the whole prefix and is named as this being one single functional group. So again, when naming the system, the carboxylic acid gets the priority. and I have a 4-carbon chain going in between these two systems. So this means I have a butane dioic acid. And in the numbering, by definition, those carboxylic acids are the 1 and the 4 position, beginning and end. So I don't need to number them. But I need to find a good way of treating this this amide. So I use its prefix. It is a carbomoyl group, and it's a carbomoyl group at the 2 position. So again, not counting this carbon in any of the chains. So this means that the whole system is a 2-carbomoyl butane dioic acid. Now, Uh, one of the big things is that as we're seeing, all of these carboxylic acid derivatives, they're all terminal functional groups, meaning that I can't put a single one of them in the middle of a carbon ring. This means I'm going to, just like I had with aldehydes, have to have kind of a different naming scheme. So if they are attached directly to the ring, what we're going to do is have a different name for each one. So we're going to include both the name of the ring and the name of the functional group. So if I have a carboxylic acid, this means I'm going to have a cycloaxane carboxylic acid. If I have a cyclic amine, it's going to be that cycloalkane name and carboxamide. So again, both cases, carbox, indicating that carbonyl group, ic acid, amide. Now, if I have a nitrile, again, very similar. It'd be a cycloalkane carbonitrile. So again, carbo really indicating that it's an attached group. So when we're numbering this, again, by definition, each of these groups will get the priority. So the carbon attached to them gets the C1 position. So working through the name, I've got a cyclohexane carboxylic acid, and then I just go ahead and throw in that 3-oxo. Next case, this one gets a little bit fun because I have a cyclopentene carboxamide. So in this case, I have to add in that 2 to indicate the position of that alkene. Last case is comparatively simple. I have a cyclobutane carbonitrile. So again, when you work through this through the naming schemes, it's not quite as bad. All right, this brings us to our final family of functional groups. These are the esters and the acid anhydrides. So again, both of these have this CO2 motif linking together carbon chains. Only different is the acid anhydrides. You can almost think of combining 2 esters. So both of these groups can be classified as carboxylic acid derivatives, as you can go ahead and turn them back into carboxylic acids in water under acidic conditions. However, both of these functional groups do follow their own unique naming rules because they're somewhere in between acting like an ether and acting like a traditional carboxylic acid. So in both cases, these molecules are going to be broken down into essentially the chunk containing the carbonyl group and the other substituent. So in the case of esters, we call this main chunk the alkanoate group. So again, I have an alkane, and that O8 is also a name for a deprotonated carboxylic acid. And then, just like an ether, I can treat the species on the other side of the oxygen simply as an alkyl group. So, working through naming an ester, we're going to name it through 2 portions. First, we're going to identify what our alkanoate portion is. Then we're going to go ahead and number both the alkanoate and alkyl chains, identifying our main groups. And again, in each case, that carbon next to the bridging oxygen is going to be receiving that C1 designation. Then we're going to establish the root name of the alkyl substituent. Then we're going to write the parent name in the format of alkyl, starting with the alkyl substituent, and then alkanoate. So always alkyl, alkanoate. And then we're going to add the names of the substituents and locator numbers according to our previous sets of rules. And again, note substituents can appear both on the alkyl portion and on the alkanoate portion. So let's go ahead and go through our system. So in this case, I have an ester, so I know I'm going to use that alkanoate. Now, my alkanoate is going to be on the left, and I have a 4-carbon chain, so I have a butane, meaning I have a butanoate. So whatever else, I've got a butanoate. Now let's do the numbering. So again, numbering my butanoate, 1, 2, 3, 4. Now, one of the things to watch out on the alkyl portion is note that carbon attached to the oxygen gets the 1, even though this essentially shortens my longest chain. So I got 1, 2, 3. This means that my other group is propyl, not the butyl you may have anticipated. Meaning this molecule is a propyl butanoate. But note, both groups have a functional group. My butanoate has a ketone, and my propyl group has an alkyl substituent. So to name that ketone, this would be a 3-oxo group for the ketone, and for the propyl, I have a 1-methyl group. So putting these both together, I have a 1-methyl propyl, 3-oxobutanoate. So again, taking a complex molecule and a complex name and breaking it into chunks. Now, acid anhydrides are a little bit kind of more interesting because their name comes from the fact that you can synthesize them by taking 2 carboxylic acids and kind of shoving them together, removing a water. These are called dehydration reactions because I'm dehydrating. I removed a water from the molecule. So when we're naming these acid anhydrides, what we do is we identify them based on the identity of these 2 groups, which are known as alkanoic groups. So again, alkanoate becomes alkanoic, again, indicating they came from an acid, that oic suffix. So again, we can split these into 2 main classes. They can either be symmetric if these 2 R groups are identical, or asymmetric. And we name both of these slightly different. So let's start with the simpler symmetric case. So for a symmetric acid anhydride, we're going to name the molecule according to the function alkanoic anhydride. So everybody's going to have this anhydride, and the alkanoic name will identify what that alkanoate group would be. So in this case, since I've got an acid anhydride, it means I have an oic anhydride. Now I have to identify what that root name is. So in this case, it's going to be a propane, 3-carbon chain. So this becomes a nice propanoic anhydride. Again, because you could turn this into a propanoic acid. Now, for the next species, I did this as an identifier of a name that your book doesn't quite cover quite as well. Because again, I still have that acid anhydride. So I've got an oic anhydride. So in this case, my root that's bound to it is going to be a benzene. But when we name benzene-based acids, they get their own kind of fun name. They're called benzoic acids. So this means that this becomes a benzoic anhydride. Now, when numbering this system, in case I place substituents on it, we're going to give that 1 priority to the carbon bound to the anhydride. So again, very similar to treating this as a cyclohexane-based acid. And again, given the 1 position, working our way through. But again, we never need to name that 1 position because by default, it's terminal. Now, this brings us to our last species, a nice branched alkane. So again, still an acid anhydride, still going to be oic anhydride, still symmetric. In this case, we have a 4-carbon chain as our principal chain, 1, 2, 3, 4. So I have a butanoic anhydride. Now numbering this, here's our main chain, and now we have to name that methyl group. So it's a 2-methyl butanoic anhydride. And note, we only have 1 name before that anhydride because it's the identical substituent on both halves. Now, what happens when I get to an asymmetric case? So in an asymmetric case, my 2 alkanoic substituents are different. So I'm going to name it twice, once for the first alkanoic group and once for the second. Now, when naming this, each is going to correspond to what the carboxylic acid would be. So again, if it would be a benzoic acid, it would be a benzoic group. An ethanoic acid, an ethanoic group, and so on and so forth. Now, when figuring out which one goes first, well, we rely on our good old standard alphabetically. First one to show up alphabetically is the one that goes first. So let's name our first species. So we have an acid anhydride, so I'm going to have that oic anhydride. And on one group, I have an ethane species. And on the other one, I have a benzene. So that ethane becomes ethanoic, and that benzene becomes benzoic. So this one, B before E, benzoic, ethanoic, anhydride. And then again, if I need to number the system for the alkyl version, for the chain version, that one position goes to the oxygen. For benzene or cyclohexanes, that one position goes to the ring. And then in a nice kind of fun branch case, again, we have an acid anhydride. This time it's asymmetric. The root name on the left is a 4-carbon chain. So we have 1, 2, 3 is a 3-carbon chain. So we have propane. But on the right side, we also have a 3-carbon chain. So propane, propane. But remember, one of them has a substituent. So our base name would be propanoic, propanoic. Then we need to add in that substituent. So again, numbering 1, 2, 3, 1, 2, 3. On one of them, I have a methyl group on the 2 position. I'm going to put that on the one that goes first because this becomes a 2-methyl propanoic propanoic. Again, following alphabetical rules. So that brings us to the end of our functional groups and the end of our lectures on nomenclature. Take care and best of luck naming.